Now we've made pretty good progress here because we've really got these unique solutions for these different components of the universe. However, there is a caveat. The universe consists of multiple components. i.e. the fact that there is matter and light already tells us that there is radiation and matter that we need to consider. And this is a spoiler because this week's lecture is about solving the Friedmann equation. Next week's lecture is an observational one about how we actually go about measuring the parameters of the universe that we've described today. So, spoilers. The actual universe that we're in at the moment has something like omega m, matter density 0.23, omega r of order 10 to the minus 4. In other words, there are photons, but they're not very important, and omega lambda equals 0.73. So in fact, despite what I've said about it's really not obvious why there should be a cosmological constant, there seems to be one. It actually seems to be the dominant component of the universe. You'll also notice that omega total equals omega m plus omega r plus omega lambda is equal to 1. So the universe appears to be flat. But it's also not dominated by a single thing that means that these solutions which we've just derived are in fact the accurate description of what's going on. On the other hand, they're not a bad approximation for a good chunk of the time. But you'll bear in mind the following. The evolution of the densities with scale factor is different. So the fact that now, for example, radiation is much less important than matter doesn't mean that that was always the case. So there are different dependencies on the density with the scale factor. And we know how they scale because we know that omega m scales as 1 over a cubed, omega r scales as 1 over a to the 4. And omega lambda is a constant. So let's just say the following. There's the point of equality. We can look at the point where omega, we're not doing well at writing today, omega m0 over a cubed is equal to omega r0 over a to the 4. It gives a of matter, radiation, a scale factor at which matter and radiation contributed equally, omega r0 over omega m0, and it's something a few times 10 to the minus 4. So, deep back in the past, in the early universe, radiation contributed much more than matter or lambda. We can also look at matter lambda equality, i.e. omega m0 over a cubed is equal to omega lambda 0. So omega m0 over omega lambda 0 to the 1/3 is equal to this a m lambda, and that's about 0.72. So the matter radiation equality happened in the dim and distant past, way back in the early universe, before the emission of the cosmic microwave background, really way back. On the other hand, matter and lambda were equivalent when the universe was about 3/4 of its current size. So that transition was quite recent. On cosmological timescales. And in principle, and I do this in the PDF, but you don't need to go through the details of it right now. In principle, therefore, I need to solve the Friedmann equation for all of these different things. And that means I need to write it down in a form where I can in fact solve it. And I say I do this in the PDF notes, you don't need to worry too much about it now. The point being, when you do that, there is no analytical solution for more than two components. So you have to do this numerically. But, and this I think is the most important point, for most of cosmic history, one component has dominated. So in other words, in the early universe, we had radiation. In the mid-universe, or the middle-aged universe, and here, radiation, this is scale factors less than 10 to the minus 4 of today, and the mid-universe is matter, and that's, say, 10 to the minus 4 to 0.5 or something like that. And then the late universe, i.e. up to today, is lambda. And so, although in principle there are places where you really have to worry about the contributions of all three and solve them, there is actually a much simpler solution, which is to say what we can actually worry about is just the relevant component at each of these epochs. And so if we wanted to draw the real history of the universe, I'll put that in inverted commas, and I plot this now again as some form of t, you know, in a sort of semi-log scale versus a of t. What I actually have is I have a period of radiation dominated, maybe I should do this as log t, a period of radiation dominated expansion, so it's actually slowing down quite quickly, a period of matter dominated expansion, slowing down less quickly, followed by, that's not meant to be a straight line, it's an exponential. It's just my software trying to be clever. Followed by this exponential moving away. So you have three distinct periods. Radiation, here this is A is 10 to the minus 4. You have matter, this is A is 0.5. And then you have lambda. And what that means is that for any given universe model that I come up with, and I can make up whatever densities of matter, radiation, lambda I want, I have a prediction about how the scale factor of the universe should have evolved with cosmic time. And so what that means is, importantly for any, branch of exact science, I can make predictions and I can make measurements about what is actually going on. And so next time We care about the observations of the universe and what they tell us about this benchmark model.